Now let's go ahead and make some observations about these graphs. These observations will be true for all graphs of the form b to the x. However, these two graphs on the right of 3 to the x and 2 to the x are more similar to one another than the graphs of 1/3 to the x and 1/2 to the x. And the important distinction here that makes them more alike is the base b. So I'm going to characterize, or perhaps describe, these graphs in terms of the base b. So we'll put the graph of b to the x, its properties with b between 0 and 1 on the left, and we'll put properties of b to the x where b is bigger than 1 on the right. Now some of these properties will be true no matter if b is between 0 and 1 or bigger than 1, but some of them will not. Now whenever you want to describe a graph, some of the most useful things to describe are the domains and ranges. And the domains and ranges for both of these are going to be the same. So to identify what the domain of these functions is, you have to ask yourselves for which x values are these functions defined. And these functions are defined for all x values. So for example, if you wanted to do 2 to some power, you can put any number here for that power. You can put positive numbers, negative numbers. Any x value will lead to an output. Contrast that with, for example, the square root of something where you can only put non-negative numbers in order to get an output. Okay, so that's our first observation, is the domain is all real numbers. Or you could say equivalently that the domain is -infinity, infinity. Those mean the exact same thing. And as you can see here, I'm putting things that are true for both of these types of functions in the middle. If there's something that's true for only one function, I'll put it on that function's respective side. Now let's identify the range of these functions. Looking at the graph, to identify the range, we're asking ourselves what y values are attained by these functions. An easy way to be able to tell if a function attains a certain y value is to draw a horizontal line at that y value. So I've drawn a horizontal line at the y value, which is a little less than 4, and this horizontal line crosses all of these functions. And what that tells me is 4 is indeed part of the range of these functions. So I can draw y value a little less than 2, and again, I see that this y value is in the range of these functions. If I draw a horizontal line at the y value of 0, then I do not get a crossing. These functions get very, very close to the line y equals 0, otherwise known as the x-axis, but we don't get a crossing, so 0 will not be in the range. And similarly for all of the y values which are negative, there is no crossing. So the conclusion of this would be that the range is all the positive numbers, because any positive y value for which you draw a horizontal line will have a crossing. And so the range will be the same for both of these. The range is all positive numbers, which is all numbers greater than 0. So we can write that in interval notation, 0, infinity. And I'm going to put a parentheses here to indicate that I'm not including 0 in the range. If I had put a bracket, then that would say 0 is in the range. Now I'll make some observations that are different for each function. So let's ask ourselves what happens as x goes to infinity. In other words, as x gets really, really large. Looking at my functions here, let's go ahead and erase these lines. For something like 1/2 to the x and 1/3 to the x, I have that the y values are getting very close to the x-axis. That is, the y values are getting very close to 0. And so I would conclude that as x goes to infinity, y goes to 0. What happens as x goes to infinity for 2 to the x and 3 to the x? Well, the y values get very large. And so I would conclude that as x goes to infinity, y goes to infinity. Now, as x goes to minus infinity, for the function which is like 1/2 to the x or 1/3 to the x, the y values are getting very large as the x values go to the left. Whereas for 2 to the x and 3 to the x, as we move to the left, the y values get very, very close to 0. And so we would say as x goes to infinity for bases between 0 and 1, y will go to infinity. And by infinity, I mean as x goes to negative infinity, y goes to infinity. And as x goes to minus infinity for b to the x where b is bigger than 1, we see that y goes to 0. This discussion is known as a discussion of the end behavior of functions. Let's make a couple more observations. First, for 2 to the x and 3 to the x, their graphs are always increasing. That is, as you move to the right, the y values are going up. For 1/2 to the x and 1/3 to the x, they are always decreasing. So as you move to the right, their y values are always going down. So always decreasing, and I'll just put a down sign or a downward arrow, and always increasing. And finally, we'll end with a couple properties that are shared by both of these graphs. First, y equals 0 is what's called the horizontal asymptote. That's true for both of these graphs. That means that as either x goes to positive infinity or minus infinity, either one, the y values get really close to 0. Now, for 2 to the x and 3 to the x, as x goes to minus infinity, the y values get really close to 0. And for 1/2 to the x and 1/3 to the x, as x goes to positive infinity, their y values get close to 0. But the important thing to say in terms of the horizontal asymptote is that in one direction, it doesn't have to be both, it just has to be either to the plus infinity or to the minus infinity direction, the y values get very close to 0. And that makes y equals 0 a horizontal asymptote for all of these functions. And finally, the last thing I want to point out about these functions is they all go through the point 0, 1. So 0, 1 is on the graph for all these functions. Another way to say that exact same statement is that the y-intercept is 1.